In this video, you'll see how we factor special cases of polynomials. So let's remember what perfect square trinomials are. In a perfect square trinomial, the first and last terms are perfect squared. I've got an a squared and a b squared in the examples above. And that middle term is twice the product of one factor from the first term and one factor from the second term. So let's take a look at how I could factor this. N squared minus 12n plus 36. The first thing that I notice is these are both perfect squares. So I think to myself, this could be a perfect square trinomial. Do I get that middle term? Can I get this by multiplying 2 times a times b? Well, my a in this example is 1, and my b, since 36 is b squared, my b could be negative 6. So 2 times 1 times negative 6, I get negative 12. So my perfect square trinomial, when I factor this, is going to be n minus 6 times n minus 6, or n minus 6 squared. All right, let's take a look at the second example. Well, when I look here, the first and last terms don't look to be like they're perfect squares. But if I factor a 3 from every single term in that trinomial, I get x squared plus 6x plus 9, and now that first and last term, they are perfect squares. So I could rewrite this as 3 times x plus 3 times x plus 3, or 3 times x plus 3 squared. All right, here are a couple for you to try on your own. First one here, these two are perfect squares, so I'm going to try to factor this, knowing what I know about perfect squares. So 16n squared, the square root of that is 4n. 81, the square root of that is 9. If I take 2 times 4 times 9, I get 72. So my two binomials are 4n plus 9 and 4n plus 9. So 4n plus 9 squared. My second example here, I am going to factor out a 2 first. And I get m squared minus 14m plus 49. I see the first and last terms here are both perfect squares. Well, m, and then 49, the square root of 49 is 7. I see I'm subtracting 14m, so 2 times 1 times 7, that's 14, and it will be negative if I put a minus sign here. So 2m minus 7 squared. And then we had the difference of two squares, a squared minus b squared. Remember, that will factor to a plus b times a minus b. So my first example, n squared minus 100, I see those are two perfect squares. I can factor this, n squared is going to become n, and then minus 100, the square root of 100 is 10. But how do I get negative 100? It's going to be a positive 10 times a negative 10. And then let's look at 8n cubed minus 72n. The first thing I want to do is I want to factor out the greatest common factor. That's going to be an 8n. I get n squared minus 9. And now that's the difference of two squares. So 8n times n plus 3, n minus 3. All right, here are some for you to practice on your own. And that was Thomas James Romero, the one and only for you. All right, first one here, 16y squared minus 81. I've got two perfect squares here, so I've got 16y squared. The square root of that is going to be 4y. And then the square root of 81 is 9. So 4y plus 9, 4y minus 9. 12m squared minus 48. I want to pull out the GCF first. This might help me see if this is a difference of perfect squares. 12 is the GCF. I've got m squared minus 4. Yes, that is the difference of squares. 12 times m plus 2, m minus 2. All right, let's take a look at this one. It's a bit more challenging. I see the coefficients, and those are perfect squares, but what about those exponents there? When I think about this problem, I try to rewrite this. So I'm going to rewrite 4y to the 6th as 2y to the 3rd, but then if I square that whole quantity, now it's going to equal 4y to the 6th. So I'm just rewriting this. 121 n to the 4th. I could rewrite this as 11n squared, but now if I square that quantity, I get 121 n to the 4th. And now this is the difference of perfect squares. So I could rewrite this as 2y to the 3rd plus 11n squared times 2y to the 3rd minus 11n squared. And if I multiply those two binomials, I will end up back at that original problem. All right, here's one for you to try on your own. I want to know how much taller is the larger square. Well, I know that small square is a 5 by 5 square because the area is 25. And then I look at that large square, and I see this is a perfect square trinomial. I'm going to have x plus 7 and x plus 7. So, how much larger is the larger square? Well, or how much taller, excuse me. The height is x plus 7, and if I subtract 5, the height of the smaller square, it's going to be x plus 2. All right, I give you an expression for the volume of this rectangular prism, and I want you to find the dimensions. I want you to find the length, the width, and the height. So when I'm looking to do that, the first thing I'm going to do is I'm going to think to myself, how can I factor this expression? Well, 27n squared minus 48, they have a common factor of 3. I get 9n squared minus 16. And then do you notice that that's the difference of perfect squares? So it's going to be 3 times 3n minus 4, and then 3n plus 4. So these are the dimensions of my rectangular prism. 3, and then on the other side is 3n minus 4, and the third side is 3n plus 4. All right, you can write any expression that's a perfect square trinomial. And now, write any expression that is the difference of perfect squares. Try not to use one that I gave you before. All right, can you rewrite x to the 4th minus y to the 4th so that it is the difference of two squares? And then I'm going to ask that you factor that expression completely. So first things first, x to the 4th minus y to the 4th. I could rewrite x to the 4th as x squared squared. Now that's a perfect square. Minus y squared squared. And that's how I could rewrite the expression. And now I want to factor that expression completely. So it's going to be x squared plus y squared times x squared minus y squared. Now you'd be forgiven if you stopped right there, but guess what? That second factor is also the difference of perfect squares. So to factor this completely, x squared minus y squared, that's going to be x plus y times x minus y. Tricky, tricky one. And that's how we factor those special cases.